Okay, everyone, thank you for coming to the final installment of this ONEPAS Thematic Series, which has been focused on the mathematics of thin structures. Our last speaker here in the series is Cyrill Muratov from the New Jersey Institute of Technology. And as you can see, he'll be telling us about one-dimensional domain walls in thin film ferromagnets. Cyrill, the floor is yours.
Okay, well, thank you very much, Ian, and thank you for this invitation. It's a very nice opportunity for me to present a little overview of the work that I've been doing in the field of micromagnetics over the last 15 or so years. So I'll tell you about some of this work, and since time is short, it will be mostly an overview of the results. Okay, but let me mention first that this work wouldn't be possible without a great number of friends and collaborators, which are listed here. And in particular, this work has involved a significant number of young researchers. So I can mention 6 postdocs. And 2 of them are current, and Giovanni is one of them who is in the audience, and also it involves a number of PhD students. And I'm going to mention some of the results that on the joint work with Philip Rybakov in particular, and some work with Florian Nolte. And in this group, the work, I should mention the joint work with Milena Kermisi, Ross Land, and Giovanni Di Frato. Okay, so this is going to be a talk about modeling of ferromagnetic materials. So very briefly, magnetism is a physical effect that has to do with a spin degree of freedom of electrons, and it's a quantum mechanical effect, which is due to the Coulombic interaction between electrons in metals, and it's certain electrons in metals, and because it is closely related to the Pauli exclusion principle. And this interaction results in the tendency of adjacent electrons, the spins of the adjacent electrons, which are can be thought of some kind of rotational rotation of a particle. So these spins tend to align. And if this interaction is sufficiently strong compared to the thermal effects, then this produces a phase transition below a Curie temperature. The material acquires a macroscopic magnetization. Magnetization refers to the density of is the average density of magnetic moments of individual spins, and so we go from a situation where the magnetic moments of particles are oriented at random to the case where they are aligned together due to the exchange interaction, producing a macroscopic magnetization. Now, one could, from the point of view of magnetism, one could view individual electrons as tiny dipoles, and when the dipoles are aligned in series, so to say, they generate a net magnetic field, and that is what is observed as a macroscopic manifestation of magnetism. And this in particular results in the long-range interactions between different magnets. So if we take a magnet, we take 2 bar magnets and put them next to each other with the opposite poles close together, then these magnets will experience attractive interaction. So that would be an energetically favorable configuration. And if we put the light poles close to each other, then similar we see repulsion corresponding to the unfavorable configuration. And well, what about this type of configuration when we have two bar magnets that are anti-parallel in a vertical arrangement? Well, I would have asked if it was a live audience, but let me give you an answer. The magnets actually would attract, and you can think of it as that this is because the opposite poles are closer to each other than the like poles. Okay. So, however, this immediately illustrates an issue that arises in ferromagnetism that creates that makes the ferromagnetic materials so interesting from the point of view of pattern formation. If you look at these first two examples, clearly from the dipolar interaction point of view, magnets are better off aligned. So a ferromagnetic state here minimizes not only the microscopic exchange interaction between the electrons, but also the magnetostatic interactions between the dipoles. However, if we have a ferromagnet which is in which the magnetization is pointing sort of vertically in a slab, then clearly in a film there is a competition between the exchange interaction, which wants these spins to be aligned, and the dipolar interaction, which wants them to be anti-aligned. So the magnetostatic interactions frustrate the ferromagnetic order, and this gives rise to an incredibly diverse array of magnetic of the magnetization patterns, which are called magnetic domains. This is just a sample of various observations, experimental observations of domains, and basically what you see here is some components of the magnetization vector measured on the surface of a material, and you can see that there is an incredibly rich variety of patterns that don't seem to be similar to one another. And one might ask if there is some kind of a general principle in the organization of magnetic domains, and it's unlikely, well, except maybe one general rule that the magnetic patterns want to follow is the so-called principle of pole avoidance. And basically a way to minimize the magnetostatic energies is to reduce as much as possible the presence of magnetic charges. I will talk about it a little more, but the magnetic charges is basically the distributional divergence of the magnetization vector. So let's look at this familiar example here of a rectangular or square thin film sample where the magnetization lies in the film plane and takes only four possible values inside the film. But keep in mind that outside the film there's no material, so therefore the magnetization is zero. Okay, so and it is easy to see that that's actually a divergence-free magnetization pattern, which creates no poles, no distributional divergence of the magnetization. Indeed, since the magnetization is piecewise constant, this is the distributional divergence is just concentrated on the jumps of the magnetization is equal to the jump is given by the normal component of the magnetization along the jump, and you can see that, I mean, the jump of the normal component. So you can see that in all of these four discontinuities, the magnetization, the normal component of the magnetization remains fixed. And similarly, at the sample A edges, the magnetization is tangential, and therefore there is no normal component, and there is no normal jump of the normal component. So, and this is also an example of a pattern that is recurrent in ferromagnetic materials. This is called a pattern of magnetic domains. And what these patterns typically consist of are large regions of space in which the magnetization is essentially constant, separated by narrow transition regions where the magnetization changes abruptly from one constant value to the other. These are what is called the domain walls, the magnetic domain walls, and these are magnetic domains. And my talk is going to be about trying to understand the domain walls separating the magnetic domains. And okay, so this is the story when the magnetization lies in plane. Actually, when the magnetization tends to align and anti-align with the normal to the normal direction of to the ferromagnetic film, the interpretation becomes more complicated, and this situation gives rise to a whole other array of patterns, and I will not be talking about this here at all. So if you'd like to learn more about that direction of the work that we've been doing recently, and which is motivated by some exciting developments in ferromagnetic materials, please come to my talk on May 25th at the Siam Materials Meeting. Okay, so there is a very well-established modeling framework for studying magnetization patterns, which this is called a micromagnetic modeling framework. It's been introduced by Landau and Lifshitz in 1935 and has been developed by many people, and I just list here a few key names. And that in particular, let me mention that the term micromagnetics itself is due to Brown from the 1960s, and the sort of the micromagnetic point of view of the physicists on the mechanisms, observations of magnetic domain patterns is really nicely summarized in this Bible of magnetic domain physics. This is the book of Hubert and Schaefer from 1998, which actually served as a bridge for the mathematical community, which entered around that time into the area, and there was an explosion of studies in rigorous mathematical analysis of problems in micromagnetics, and this work has been nicely summarized in this review of the Simone, Kohn, Müller, and Otto. So the micromagnetics is based on the energy functional, which is called the micromagnetic energy functional, which is what we have here. So it's a functional defined on the magnetization. Magnetization is a function defined on a three-dimensional set omega, which is a vector valued with a constraint on the length of the vector. Okay, so this length of this vector is referred to as saturation magnetization, and the energy consists of the exchange part, which is penalizing the spatial variation of the magnetization. Here I'm using uniaxial anisotropy energy. It's an energy that is causing some preferred orientation in a single crystal. Ferromagnetic single crystal, which I have here, the Zeeman energy, which is the tendency of the magnetization to align with the field. And the most interesting term in the energy is this so-called demagnetizing energy, or the stray field energy, and I will talk about it a bit shortly. But let me say that from this energy, one can obtain a number of descriptions of magnetization patterns, such as the statics, so the observed magnetic domains can be interpreted as either local or global energy minimizers of the micromagnetic energy. Then the dynamics of the magnetization it is similarly described by the Landau-Lifshitz-Gilbert equation, which is some kind of a damped wave equation driven by the micromagnetic energy, and stochasticity can also be added. When I said that this theory is mesoscopic, what I mean is that at the level of formulation of the problem, thermal fluctuations don't enter into the description, but in fact, a posteriori, small fluctuations can be added, and this is why, in particular, one could also be interested in studying saddle point solutions associated with the micromagnetic energy.
So,
now,
sorry, can I just ask one question? So,
yes.
so the H in the previous energy functional is given, right?
Yes, it's an applied external field. Yes.
And so outside of omega, it satisfies like static Maxwell or something like that.
Yeah, exactly.
Okay. So is there any connection then between the choice of, I guess in this setup, it's E2 is the preferred direction? Like, is there any alignment between that and H, or are they completely?
No, H is completely independent, but of course I just chose an example of a uniaxial ferromagnet with a particular orientation of the axis.
Okay.
Of course, there is a lot of variety in there.
Okay. Okay. Thank you.
All right. So the stray field energy, one can understand it. It's an energy of interacting dipoles. Okay. And interacting by Coulombic interaction. So there is a complete analogy with electrostatics in which the magnetization would be replaced by polarization, dielectric polarization. And it is well known that the dielectric polarization is the negative divergence of the dielectric polarization is the density of the bound charges in a dielectric. So even though there are no magnetic charges, one could still think of the divergence of the magnetization as a sort of a magnetic charge, okay? And in this way, this energy is simply the Coulombic energy of the magnetic charges. Of course, one could then use this. So this is one definition, which is particularly transparent. And then one could use this definition to then, and properties of Coulombic kernel to express the stray field energy as an integral over the magnetic field or the magnetic field squared, expressed through the magnetostatic potential. Okay, and this formulation leads to the basic static Maxwell's equations with the constitutive relationship between the magnetic field strength B and magnetic field B and magnetic field H. And let me mention that there is actually an alternative way to do this, to formulate the energy, and that is to introduce a vector potential whose curl is B. And then the vector potential can be similarly expressed in terms of curl M in the Coulombic gauge. One would be in particular interested if there are specific variational principles associated with the magnetostatic energy, because the way I introduced it to you, it's just a function of M, but it's a non-local functional of M. So a natural question is whether there are some local formulations, variational formulations associated with the stray field energy, and there are. And the one that is fairly well known is a minimax principle in which we minimize the energy with respect to M, but the stray field itself, stray field energy is the maximum of the following energy functional. And so this gives rise to a minimax problem where the solution over scalar magnetostatic potentials, whose solution gives the magnetostatic potential of the problem. But let me mention that another representation using the vector potential allows to rewrite the stray field energy as a square of the difference of the curl of the vector potential and the magnetization. which leads to the following alternative minimization principle for the stray field energy. And this is something which is not as well known, but actually was used, was discovered a lot in the finite element community doing simulations of in magnetism. And what we noticed is that actually okay, so this is a minimization principle which could be combined with the minimization of other terms in the energy, but there is an unpleasant divergence free constraint on the stray field here on the vector potential, so which is may not be easy to handle, but actually it's not so difficult to see that this variational method is equivalent to minimizing the energy function, which is written over here, and that is our result of our recent work with Giovanni Di Ferrata and Filippo Bakov and Valery Slastikov. And here, essentially, we can remove the divergence constraint and we recover it as a result of the minimization. Okay, now back to micromagnetics. The first.
Excuse me, in the previous slide, what is ms square v? The new minimization principle. What is v in that?
Where v is the volume of it's just a measure of omega.
Okay. Okay.
Just
Thank you. Sorry to interrupt.
Here, yeah, and use the fact that m has constant length. Okay.
Okay. Okay.
All right. So the first application of micromagnetics was to understand the structure of the simplest domain wall between opposite orientation of magnetization. And the simplest such a domain wall solution is called the Bloch wall. In the Bloch wall, the magnetization rotates by 180 degrees between the two easy axis orientations, which in my case, my talk will always be the y-axis. And this rotation occurs in the plane perpendicular to the direction of the wall. Okay. Now this wall is called the Bloch wall, but actually Bloch, who introduced the idea of transition layers in 1932, actually didn't study this problem. And in fact, looking at his original paper, I discovered that he was actually the person who first calculated the domain wall solution for the Ginzburg-Landau energy. Okay, so the people who really solved this problem for the first time were Landau and Lifshitz, and they simply said, well, the wall has to have a particular rotation. Well, it has to have a particular structure like this in order to minimize the presence of charges. So one could indeed do a rotation in the YZ plane and thereby making the divergence of the magnetization zero. And so plugging in this ansatz, so that obviously minimizes the magnetic field term. So plugging in the ansatz one could then minimize. One obtains the Euler-Lagrange equation, whose solution is this simple expression. Okay, and so the physicists are done and happy in this case. So this is the Bloch wall profile. But of course, as mathematicians, we start wondering, well, okay, well, is this the only solution? Is this the energy minimizing solution? What kind of other solutions are there? Is the solution supposed to be one-dimensional, and so on? And just a brief remark is that Néel rediscovered this solution in 1944 unknowingly, and among other solutions that he also considered with similar type of ansatzes. And he noted that in the case of one-dimensional profiles, Maxwell's equation for the magnetic field can actually be solved. And this gives rise, and in this case, that the stray field is simply equal to M1. Okay, and so the contribution if we do not make this ansatz here, the contribution for a one-dimensional profile of the stray field energy will be simply an effective anisotropy term. Okay, now how do we know that actually this is a energy minimizing profile? Well, this is a nice and simple exercise in calculus of variations, and so let me show you how this works. So remember, so first of all, let's normalize the magnetization to be a unit length vector, okay? And so the first observation is that since we have a unit length constraint, we can relate the gradient squared of the second, the derivative of the second component of magnetization in terms of the other two. And if we just use Cauchy-Schwarz, we obtain this inequality here. So this inequality allows us then to estimate the exchange energy from below by just the energy associated, by this energy associated with the derivative of the second component. Okay, then of course we can, if we want to obtain a lower bound, we can just drop the contribution of the stray field, so that's gone, and then we use again the unit length constraint, so we end up with this much simpler energy formula. But then we can apply the Modica-Mortala trick by completing the square and make a further simplification, and then use the fact that M2 changes from -1 to 1. And obtain the energy here, which is exactly the energy of the Bloch wall. And so, therefore, we see that the Bloch wall is indeed a minimizer because it saturates this inequality, and in fact, it's a unique minimizer. And one could similarly show that not only is this is a unique minimizer in 1D, but it's also a unique minimizer, for example, in a periodic setting in 3D. Okay, so that's nice, but this leads naturally to a question of the kind that appears in the studies related to the famous Giorgi conjecture, and I would call it a magnetic Giorgi conjecture. So let's suppose we look at any critical point of the micromagnetic energy that is for which the component of the magnetization along the easy axis is monotone from -1 to 1 in one direction. Is the solution then the Bloch wall? Okay, or a rotation of a Bloch wall. Now notice that in the Giorgi conjecture, when one looks at the solutions of the scalar equation, Laplacian u equals f of u, where f is a bistable, say u minus u cubed, let's say, with the right sign, an answer to this question under suitable assumptions would be not just a single one-dimensional profile, but actually all possible rotations of such admissible rotations of such profile. Now here, if you think about it for a second, not every rotation is possible anymore, because if we rotate the profile in such a way that the direction of the wall makes an angle not equal, becomes non-orthogonal to the easy axis, then we pick up an additional contribution from the stray field, and so the energy would go up strictly, and in fact even it would be infinity. So there is also some kind of a selection that happens. So the Giorgi conjecture of the type that we're used to for Ginzburg-Landau problems will surely not be valid in this setting. Okay, so now I'm going to go back and go to the thin films. And so when we were talking about the Bloch walls, we were of course talking about solutions in the whole space, and so we were essentially ignoring the effects of the boundaries of the ferromagnet. And if we instead look at a finite slab, a slab of finite thickness, then what happens is that if we substitute the Bloch wall ansatz into the energy, we will find that although in the bulk of the material there will be no charges, charges will start appearing on the surfaces of the material because the magnetization jumps abruptly to 0 from length 1 vector there. And so this inevitably will produce some stray fields. And it was Néel who observed in 1955 that, in fact, if the width of the thickness of the film becomes sufficiently small, it is actually energetically more favorable to perform a rotation between the two directions, not in a Bloch manner, but what is now called a Néel manner, namely when the magnetization rotates in the film plane. And clearly, this kind of configuration it cannot be charge free, because in this case there is always a non-negative. There is non-zero divergence of the in-plane magnetization going across the wall. So this creates a difficulty, because in order to study domain wall solutions in thin films, one does need to properly account for the non-local nature of the stray field interaction. Okay, so how does one approach this problem? Well, micromagnetics of thin films is just a particular instance of the general framework. We take the micromagnetic energy, where I now also use some general anisotropy function, where my domain is some kind of it's a cylinder. So it has so omega is now a two-dimensional domain, and I just thicken it by finite thickness d, so I get a cylindrical domain, which you see here. Okay, and okay, so there is this energy, and in this energy there are some constants that appear. Okay, these characteristic values are given here, and there are ranges also of geometric parameters. So the film thickness, for example, can be on the order of several nanometers, while the lateral extent of the film could be tens or hundreds of nanometers. And associated with the typical values of the parameters is a special length scale, which is called the exchange length, which is obtained by balancing the exchange energy with the stray field energy. And that is on the order of about 5 nanometers in most materials. And so one could see that there is actually a rather significant, maybe a significant disparity between the natural length scale of about 5 nanometers with the film thickness and film's lateral extent. So this creates a formidably difficult variational problem. Okay, so it's a vectorial problem. It is a nonlinear variational problem. Well, it's mainly due to the unit length constraint on the magnetization vector. It is non-local due to the stray field. It has multiple scales, so it can be quite stiff. And also something that I didn't mention here, one could be interested in magnetization patterns that are characterized by non-trivial topological characteristics. So there are also topological constraints. So in order to make sense of these kinds of problems, one really needs to find a compromise, which is a class of models that retains essential features of the physics of the problem, but at the same time captures the properties of the phenomena in question. And so the solution to that is obtained by using rigorous asymptotic analysis methods of calculus of variations, which I'm going to introduce to you briefly. Okay, so what we will do as a first step is we are going to undertake a dimension reduction, where we want to go from a 3-dimensional problem to a 2-dimensional problem, where the magnetization is just a function of 2 spatial variables. And so it is reasonable to suppose that the magnetization in a very thin, and we are going to take advantage of small thickness of sufficiently small thickness of the film. So if the film is sufficiently thin, then it is reasonable to suppose that the magnetization hardly varies in the thickness direction. So if we just introduce an ansatz of a magnetization that varies only in the x and y direction, then we get exactly this energy functional normalized to thickness with some dimensionless parameters, and a kernel that mediates the charges, the in-plane divergence of the magnetization, which is asymptotically like a Coulombic kernel, and there are also a term which involves out-of-plane component. So the next thing you do, you put it in Fourier space, and you calculate these kernels in Fourier and do a Taylor series expansion in thickness. And to the leading order, one obtains the following energy, which now has some local part, and it has non-local contributions, one of which is just a divergence of the magnetic charges in the plane, which we will we refer to as the volume charges, and a term that involves the out-of-plane component, which is due to surface charges. Now, this I will give you a glimpse of how this can be justified through asymptotic developments by gamma expansions. But let me mention also that in this problem, in the whole space is quite, which is what I'm going to be dealing with in this talk, is this definition is quite subtle because of one needs to be careful about controlling the convergence of these integrals here. Okay, and the appropriate way to define these contributions is actually by Fourier in the natural function spaces. Let me also mention that for bounded samples, it is not enough to simply restrict these integrals to the domain of the ferromagnet. Actually, would not work for the non-local terms, and instead one would have to somehow truncate the magnetization and take into account that the magnetization is zero outside the sample. Okay, but if one simply does it naively and jumps from length 1 to length 0 vector, then it turns out that these two terms become infinite and generically become infinite. And so some care is needed in defining what exactly is meant by this, by these terms in the for the finite domain problems. And this is something we are finishing a paper on with Giovanni Di Frate and Valery Slastikov. Okay, so these kinds of calculations can be justified via gamma development. So let me give you an idea of what can be done. So let's suppose that we have a thickness, film of small thickness delta, and we define the thickness average value of magnetization. Okay, and for that thickness average value, we define then the non-local terms, and then we compare it with the full three-dimensional micromagnetic energy, and it is possible to show that the error you make by replacing the full micromagnetic energy with this one is on the order of the exchange energy times delta integrated over thickness delta. So this is more or less like order delta squared term. So this term is negligible compared to these two terms. And now how you proceed depends on the kind of limits that you are considering. But for example, imagine that you have some control on the Dirichlet energy of the three-dimensional magnetization. Then basically, as you pass to the limit of delta going to 0, you almost everywhere you recover the unit length constraint for m bar, because otherwise this is no longer unit length, and you recover the two-dimensional energy, which we saw in this has been done in a periodic setting here in our joint work with Knüpfer and Nolte. Okay, so in soft ferromagnetic materials, so the next question is what kind of limits to consider. And in soft materials, appropriate limit is to take the quality factor, which measures, let me go back. So this term here is measuring the penalty of the in-plane magnetization away from the easy axis. Okay, so we assume this to be of order delta squared together with the magnetic field, and then after appropriate rescaling, the energy is asymptotically to the leading orders given by this expression. So the magnetization is forced to line the film plane, and only the volume charge contribution survives, together with some contributions from the boundaries, where there is a large coefficient appearing here. So when delta goes to 0, that forces the magnetization to be tangential to the boundary, and these two terms drop out. And so we end up with an energy, in particular, if there is no boundary, we end up with an energy which is just the local part of the energy plus the volume charges. Okay, now we can start talking. Now that we have this model, we can start talking about uncharged, about the Néel, various Néel walls in thin ferromagnetic materials. So let me start with the most studied case of uncharged Néel walls, of which there are two types. One is the so-called 180-degree wall, and the other is the 360-degree wall or winding wall. And you can see that these are charge-free configurations because the total charge is the integral of the charge density, which is the divergence of the magnetization in the plane, and that if you integrate that over a large region, that will be just the flux of the magnetization over the boundary. And you can see that, say, taking a large rectangle here, that flux vanishes. So in other words, the magnetization doesn't jump in the normal, doesn't experience the normal jump in the normal component across the wall. Okay, and here similarly, because of the 360-degree rotation, the magnetization is returns to where it was. And so again, there's no jump. So in this situation, it is of course natural to introduce an angular variable for the magnetization, which is always possible for so in the context of solar functions, and then the energy becomes a scale, a function of one scalar variable theta. Now, what happens if we don't have any stray field effects? Well, in that case, the problem reduces to the familiar type of problem that appears in the studies of the Giorgi conjecture. And in that case, specifically, depending on the fields, or let's say we consider no applied field, it is known that all monotone solutions in one direction will be 180-degree walls and their rotations, one-dimensional. All solutions will be indeed one-dimensional. And what happens in the in the non-local problem, however, is quite different. And so let me start with talking about the 180-degree walls. So these are, which are shown here numerically and experimentally. And this problem has been studied quite a bit, and the first study of existence and qualitative properties of these domain wall solutions was done by Melker in a closely related model. So what we did is, in a joint work with Milena Kermisi and myself, is to extend the work of Melker for problems in the presence of additional applied fields, and we also sharpened some of the results of Melker. And what's important is we introduced a different approach in the analysis of minimizers. And so the way we approach this problem is to go to reduce, so we study one-dimensional profiles. So the micromagnetic energy now reduces to this energy functional, which contains this sort of Ginzburg-Landau type or Kahn-Hilliard type energy term here, and the h1/2 homogeneous norm square of the sine of the angle. Okay, and what we do is we try to minimize this energy among functions such that up to an addition of a profile which looks roughly like a domain wall profile, the resulting function belongs to H1. So in this way, we impose the asymptotic behavior of the solution at infinity to the prescribed values. Now, so why is this important? Well, because the difficulty associated with these kinds of problems is not so much that that there is some issues with regularity, lower semi-continuity. The main issue, the basic issue, is that this problem is posed on the entire on an unbounded set, and so what we need to make sure is that we recover the asymptotic, the limit behavior at infinity of the minimizing sequence after passing to the limit. Okay, and this is not a priori clear, and so what we do is we try to find a minimizing sequence which is somehow uniformly bounded up to a subtraction of a characteristic profile that has the right behavior at infinity that is uniformly bounded in H1. And that's a priori not clear at all, because of course the energy is translationally invariant, and so it's easy to imagine a minimization sequence that runs off to infinity, and in the limit you recover something trivial. Okay, so in this particular instance, it is this question may be handled by the fact that the energy is non-decreasing with respect to symmetric decreasing rearrangements of sine theta, and that allows us to reduce the problem to the study of monotone profiles in theta that go from 0 to pi, and so fixing the center of that profile allows us to pass to the limit and obtain existence of a minimizer. But what's more, we can obtain we can obtain existence, uniqueness, regularity of the minimizers. The minimizers are just classical solutions of this non-local one-dimensional PDE. Okay, and because it's non-linear and non-local, even the basic question of uniqueness is within a one-dimensional setting. For monotone solutions, it's not a priori clear. And actually, it is in a work with Xiaodong Yang, we actually managed to prove that the minimizers of this problem are indeed all monotone critical points of this problem between connecting 0 and pi are indeed in the absence of applied field are indeed the minimizers and are unique up to translations. And some similar questions have been studied in the case of semi-linear fractional PDEs, and I will refer to this work of Palatucci, Savina, and Baldinocci. But an open question that I want to raise right away, and there are many open questions in this field. What about this type of result in 2 dimensions? We have no idea whether at the moment whether this is indeed the case or not, but I would imagine that this profile is actually also the unique energy minimizing profile in a, say, periodic setting, but for now we have no proof of that. Now, one other thing to notice is that we also obtained the asymptotic decay of the solutions, and the decay is algebraic because of the presence of the non-local term, instead of the exponential, which would be what you get if this term wasn't there. And in fact, some of the interest in this problem had to do with the subtle properties of the decay of the solutions of these Néel wall solutions for the very soft films, which means that when the parameter nu is very large, and that was also the main focus of the paper of Melker and of the PhD thesis of Carlos Garcia Cervera. And we came up with a nice way, I believe, a nice way to treat this problem, which actually is even applicable to just classical PDEs of Ginzburg-Landau type. I've never seen it done. So what we did is essentially, okay, we try to linearize the problem. So we want to study clearly the decay will be governed by the linearization. So what we do is we introduce some kind of a reflection of our theta profile. So instead of being a domain wall, it is now kind of a bump, and we turn it back, so it's like some kind of a bump function. Okay, and this bump function satisfies an equation with a delta function right hand side, and we can take out the linear part of the equation, okay, and put it on one side, and whatever remains stays on the other side, and then we can invert this operator that appears due to the linearization using a Green's function, which can be computed explicitly. This is the integral formula for the Green's function, and okay, so and then we get a formula for this rho, which is equal to theta for large x, okay, and so it is given by explicitly by the Green's function, plus there's some convolution with a nonlinear bit, but the nonlinear bit has a very fast decay, so it's also like a delta function, morally. So this is just like a multiple of g, okay, And so then one could immediately see how what the decay looks like. So when x goes to infinity, for example, expanding this, you get the algebraic order. But if you fix x large and then send mu to infinity, then you get this logarithmic behavior, so consistently with what's observed. So that's another way of seeing the detailed asymptotic multiscale structure of the tail of the Néel wall. Now, for the 360-degree wall, the situation is a little bit more complicated, and so we can try to use the same procedure as before, but so the solutions that we're going to get here now are topologically non-trivial, because they're actually topological defect type solutions, because the behavior on both sides of the solution is the same, and it's just the only thing is that you have a certain winding that happens. So now I introduce this beta variable. What is beta? Beta is the angle, because actually at this point all such walls will be charge free by definition, because they connected to the same states. Okay, and so we can look at the walls that have orientation along a vector that makes an angle beta with the first coordinate axis. Okay, and so this is what we're going to minimize. But now, so we want to minimize this energy in the absence of the applied field. And now, first thing I have to say is that actual existence in such problem is not at all trivial, because, for example, if there is no stray field interaction in the problem, there is no solution, because if nu equals 0, we know the only solutions to the Euler-Lagrange equation for this problem is the 180-degree wall solution. So what happens? So it is the non-local interaction that really creates the force's existence, and one could see that by looking at a wall that is oriented along the easy axis, in which case it is possible to prove that the wall profile is monotone, and therefore the stray field energy can be estimated from below after some manipulations by the logarithm of the distance at which the value of theta equals pi/4, so sort of close to 0. Okay. And so if the wall wants to split into two 180-degree walls, which is a possibility, then that will cost a logarithmically large energy, because okay, so believe me. So then we have the following theorem, and this never-ending work with Antonio Capet and Hans Knüpfer for many years, but hopefully will be finished this year. So we have we have existence depending on the angle beta. So if beta is equal to pi/2, so the wall is along the direction of the easy axis, then there exists a minimizer of the problem for all values of nu. Okay, and it is monotone. However, if beta is between 0 and pi/2, so intermediate angles, we know only that the minimizers exist only for a certain range of values of nu, okay, sufficiently small. And this is because we no longer know whether or not the minimizers are monotone. And for beta equals 0, corresponding to the Néel situation, there are no solutions. And well, that's not all. In fact, numerically, one can see walls with higher winding numbers, and they are stable because they consist of several 360-degree walls glued together, each of which carrying a dipole moment, and dipoles in sequence attract. So this creates bound states. Now, another important class of problems, related problems, is when the magnetic crystal in anisotropy becomes fourfold. So there is not one, but two easy axes, in which case the anisotropy term will look like this, and the Euler-Lagrange equation will look corresponding to like this. So with these ideas from the analysis of 180 and 360-degree walls for the uniaxial materials, we were able to prove existence of 90-degree walls and 180-degree walls. And you can think of a 90-degree wall is a wall that corresponds to the angle beta over 4, which is what you see here. Again, this is a charge, the only charge-free wall that can connect the two states of magnetization like that. And this is a charge-free wall. And here we need to worry about the possibility of this breaking into two 90-degree walls, but these would be charged walls, and so there will be a stray field and penalty for that. Okay, and these walls are observed in numerical simulations of two-dimensional systems. So here you see some kind of a half-Landau state in material of this sort. So now, more recently, we started looking at the problem of charged Néel walls. Imagine now that we use a different angle beta, different from 0, okay? And we consider a one-dimensional configuration that connects two distinct vertical orientations. Well, it's clear that such a configuration will have a net magnetic charge in the middle of the wall. And that creates a difficulty because right away it implies that that the energy, even per unit wall, per unit length of the domain wall, even in a one-dimensional setting, will be infinite. How do we see that? Well, let's introduce the m beta, which is the projection of the magnetization vector on the x-axis here, and let's consider a problem on a finite strip. Okay, then the energy, the micromagnetic energy, can be written in this form in one dimension. Okay, and remember that in my previous slide, there was a penalty term that comes from the edge. So for in the limit of 0 thickness, the magnetization has to be forced to align along the edges of this strip. And so if we were to consider a wall that does something like this, so it has to also turn at the edges, okay? And so what we will have is we have a layer of negative charges at the edges and a layer of positive charges in the center, okay? And the stray field energy will then be the sum of the energies, interaction energies of the bulk charges with the edge charges and the interaction energy of the edge charges. And these are, yes, these are bulk edge charges, and these are edge charges. And you can see that since this kernel is logarithmic, the energy will behave asymptotically as a logarithm of W. And again, the energy would go to infinity. So even to define the energy of a charged wall, one needs to introduce a suitable renormalization of the energy, and this is currently an open problem. But now this situation is even present in the case of edge when there is no wall in the strip. Okay, so we have two magnetization values that are at an angle, and then they turn towards the easy axis. This is what this would give rise to a pair of edge walls. Now, of course, the charges are equal, so the stray field energy is finite, but and so the energy can be written in this form here, and again we get the same Euler-Lagrange equation we already saw for the Néel problem, but with Dirichlet boundary conditions, which means we have to clamp theta to be equal to the angle beta, which is corresponding to the tangent direction outside the material. Okay, and we want to understand how. So of course, for this problem there is a minimizer. Okay, we want to understand the properties of this minimizer, and as the distance between these two edges goes to infinity, and unfortunately, when that happens, these edges continue to feel each other. The energy blows up. Okay, as we already saw. So what one needs to do is one needs to somehow to subtract the leading order divergent contribution. And the way we did it is by defining this renormalized energy, in which we took the stray field energy term and we subtracted from it in the integrand a term which is just what you would expect from the stray field energy of some kind of a sample profile. Okay, once again, we take a smooth cutoff function that connects between the angle beta at the edge of the film to the angle 0, to the easy axis angle in the bulk. And this gives rise to the energy that is here, which can be rewritten only using the theta as a function of positive values of x. And now this energy looks like this. It has a term which is no longer divergent. Okay, there is a term due to this this test function, so to say, which is finite, and there is an additional potential term here. And the point is that now this potential term for large values of x can be controlled by the anisotropy term, and together this makes the energy bounded from below, because it can be the integrand can be controlled by an L1 function from below. And so in a natural admissible class, we then can define, we can specify the minimization problem. And so we have a result that for each beta and each nu, there exists a minimizer to our problem, which is bounded and converges to a multiple of n pi at infinity, which means that we cannot rule out winding in the minimizer, okay? And these minimizers, furthermore, are smooth and continuously differentiable up to the edge, okay? And in fact, they have a second derivative of theta blowing up at the edge, and this is because of the presence of the non-local term. And the Euler-Lagrange equation is now can be written in this form on half-line. And so, you know, numerically we see that there are solutions that exhibit no winding. And we can also prove that for small enough values of beta, depending on nu, the minimizer is actually unique and experiences no winding, okay? And more generally, we can see that many solutions don't exhibit winding and actually have an anomalous 1/x algebraic decay, unless the angle beta is equal to what? Well, to something to pi/2. Okay, so if we are if the wall is like this, okay. All right, so but okay, so and we see that the solutions are monotone and there is uniqueness for small enough beta. So what about more generally? Well, again, a word of caution that numerically we also find that there are many other solutions which do exhibit winding, and there are in particular solutions that are not monotone that show an overshoot. Okay, I think I am I'm more or less out of time, but if you give me 3 more minutes, I will finish.
Okay.
Okay, thanks. Okay, so finally, I want to mention a recent work that we've been doing in the direction of the charge domain walls, and that is when we look at these configurations on strips, on finite strips. And so there is no longer this issue of infinite energy, but the domain wall solutions can no longer be one-dimensional. And it is known in this situation, this is a very well-known problem, and especially it's very important for potential applications. So there are several types of walls that have been observed, and so these are just numerical simulations of such walls. So it's a vortex wall, a symmetric a transverse wall, a asymmetric transverse wall, and a winding wall showing a 360-degree rotation. So let me mention briefly our recent results in the work of with Massimiliano Morini, Matteo Novak, and Valery Slastikov on the head-to-head walls. And basically, so since I don't have time, I will only tell you in a nutshell. So we study the following reduced two-dimensional thin film energy, which incorporates the effect of the film edges, which have been regularized on the length scale, which corresponds to the thickness of the material. Okay, and this condition can be rigorously derived from more microscopic models of ferromagnetism in 2 dimensions. So the energy is like this, and it's very simple. It's just the exchange and the stray field energy, but with this normalization that kind of smoothly changes m from length 1 vector to length 0 vector on a unit strip. Okay, and so we define an appropriate function class in which we can prove existence of minimizers of this problem, which has the following properties. So there is a parameter epsilon which corresponds to the film thickness. So as thickness goes to 0, as this parameter goes to 0, this minimization problem admits a solution in the form of a minimizer in which theta goes to 0 at plus infinity and a k pi at minus infinity if and only if k is 1. So for small, and if epsilon is sufficiently small, so for small values of epsilon, the magnetization exhibits a turn by 180 degree from we don't know if it can overshoot or not, but it goes from 0 to 180 degree along the strip. And in fact, we can characterize the limiting profiles and existence, uniqueness, monotonicity, various exponential decay of solutions, and I think various other characteristics of the solutions in the limit epsilon going to 0, which leads to yet another non-local PDE problem, but my time is up, so let me stop here. Thank you.
Very nice stuff, Cyrill. Questions or comments? Everyone has the right to unmute yourself, so fire away. Stephen, go ahead.
Hi, Cyrill. Fabulous talk. Thanks for the overview. A couple of questions. One would be the relationship between some of your minimization with non-local energy and the Stefan Müller's work, because he did something similar with an H1/2 norm.
Yeah.
And I was just wondering if there was an analogy there.
Well, right. I mean, they worked on these types of problems where the H1/2 norm of the H-1/2 norm squared of the divergence appears. But somehow they were focusing on the regime of not so thin films. And that is essentially a regime where in some asymptotic limits, the magnetostatic term is the dominant term. Everything else is a perturbation. So it would be kind of like thinking about a sharp interface limit of what others don't like.
I guess it links to my second question, which is the pattern formation part. So as I recall from, say, that Müller work, they were interested in the scaling law for the periodicity of the minimizers.
Mm-hmm.
And so I think it was an epsilon 1/3 scaling law.
Well, there are many scaling laws. They are all quite sensitively dependent on the details of the problem.
Yeah. So again, I guess it was the extent to which there's sort of qualitative parallels between the methodologies. I'm just trying to understand whether or not these geometric problems.
Yeah. Okay. So first of all, our work is morally not asymptotic. This work that I was talking about is more in the spirit of analysis of PDEs, non-local PDEs, without small parameters. We do use asymptotics to derive the two-dimensional problems to be studied. Okay, this is something that's inevitable. But once this is done, essentially we have just a PDE, nonlinear, non-local PDE with fractional derivatives, and we just do the classical PDE theory analysis of PDEs, nonlinear analysis of PDEs theory for those. So we are interested in existence, uniqueness, qualitative properties, regularity, questions of that nature.
Yeah, and if I could, the second question related to the 90 degree and 180 degree domain wall. So that was, should I interpret that as a divergence free constraint on these morphologies, divergence then being 0 in that context?
Yes, that's right. That's right. I mean,
Yeah.
so this is where we have to choose this angle beta appropriately.
Yeah.
Okay.
Yeah. So my question is, have you simulated the dynamics of that problem?
Well, we did to a certain extent, but well, this is what you get, you know. So these are strong attractors. By the way, also,
yeah, I meant the large domain where you basically have a sort of a quench sort of scenario. Then you have the patterns, and then the evolution of the domains, not the final state.
Okay. In these problems, it's a little different. In here, the domains form less, let's say. So, for example, in a strip problem at the last slide, the ground state of the material is just uniform magnetization alone. So there's no pattern formation. You have to impose certain side conditions. So it's sometimes, but okay, it depends. You know, if you have a strip where the magnetization wants to lie perpendicular to the axis due to the crystalline anisotropy, then you may start having again these kind of oscillatory domains with some branching and so on. So, but it's very delicate.
So the motivation for asking was the relationship between the ratio of the edge energies. That's somehow an interesting degree of freedom, and I was just wondering whether there are degrees of freedom like that there in the problem where you can tune the relative edge energies. Yeah,
I mean, there's a lot of there's a lot of freedom. I showed you certain scaling regimes, and there are other scaling regimes which give rise to different models. And you know, this last model I showed you is an example of that. Yeah. So the limit model is fully local.
Yeah. Thanks, Cyrill.
I wanted to mention something which I thought that is I forgot to mention. This problem on 360-degree walls, the energy of the minimizers are clearly dependent on the angle. So if one wanted to do some kind of gamma convergence studies on top of this problem, one would end up with a limit problem with an anisotropic perimeter. And would be interesting. So again, questions of the Giorgi conjecture type for this problem are widely open, but actually even a problem of sharp interface limit for this problem is not understood at all.
That's a super interesting one there. Thanks.
Okay, I think maybe in the interest of time, it's a good idea to hit stop. Anyone who wants to continue talking can stick around, but let's thank Cyrill again.